Welcome to Night School Science, where curiosity drifts softly between stars and science takes its time to unfold. Tonight, we're going to ask a question that sounds almost impossible, the kind of question that might make you pause and wonder if you heard it right. Could there be another Earth, hidden somewhere in our own solar system? Not in another galaxy, not orbiting a distant star, but right here, in our cosmic neighborhood, quietly existing in a space we thought we'd already mapped and understood. It's a strange thought to hold in your mind as you settle into the quiet of evening. The idea that something as substantial as a world, perhaps even a world with continents and atmospheres, and the possibility of change, might be lurking out there in the dark, undetected by all our telescopes and calculations. We like to think we know our solar system. We've named its planets, measured their orbits, sent spacecraft to visit them. We've drawn maps and built models. And yet, the universe has a way of keeping secrets, even in our own backyard. As you lie there, wherever you are, feeling the pull of gravity holding you gently to this spinning ball of rock and water, consider for just a moment how vast even familiar space can be, how much darkness exists between the worlds we know, how easy it might be for something enormous to hide in that darkness, silent and unseen, waiting to be found. There's something oddly comforting in that uncertainty, in knowing that discovery isn't finished, that wonder still has room to grow. Tonight, we're going to drift through that possibility together. We'll explore the evidence, the theories, the mathematical whispers that suggest our solar system might harbour hidden worlds. We'll think about what it means to search for something you can't see, to deduce the existence of a planet from the subtle gravitational tugs it leaves behind. And we'll wonder, in that gentle way that helps thoughts settle and minds slow down, what it would mean if we weren't alone out here, even in the sense of sharing our sun with worlds we never knew existed. So take a breath, let your shoulders ease away from your ears, and let's begin this quiet journey into the shadows of our solar system, where planets might hide and mysteries wait patiently in the cold and the dark. The solar system we think we know is a familiar story. You probably learned it in school, the neat progression of planets marching outward from the sun like soldiers in formation. Mercury, small and scorched, hugging close to the solar fires. Venus, shrouded in toxic clouds, spinning slowly backward. Earth, our blue marble, perfectly positioned in what we call the habitable zone. Mars, the rusty desert world, cold and cratered. Then comes the Great Divide, the asteroid belt, a ring of ancient rubble that never quite became a planet. Beyond that, the giants hold court. Jupiter, massive and magnificent, with its swirling storms and dozens of moons, a solar system unto itself. Saturn, adorned with those impossible rings, a reminder that physics can be beautiful. Uranus, tipped on its side, rolling through space like a marble knocked askew. And finally, Neptune, deep blue and distant, marking what we long considered the edge of the planetary family. 8 worlds, each with its own character, its own story. A complete set, we thought, a finished puzzle. But space isn't really like that, is it? It doesn't organize itself into neat categories for our convenience. The boundaries we draw are human constructs, attempts to make sense of something that defies our need for order. And as our instruments have grown more sensitive, as we've peered deeper into the outer reaches of our solar system, we've realized that the neat story we learned might be missing chapters. Important chapters. Consider the sheer scale of the solar system. We tend to think of it as the space containing those 8 planets. But that's like thinking your house is just the rooms you use every day, ignoring the attic, the basement, the yard, stretching out beyond the fence. The planets occupy a relatively small disk of space, a flat plane extending out to Neptune's orbit, about 2.8 billion miles from the Sun. But the solar system doesn't end there, not even close. Beyond Neptune lies the Kuiper belt, a vast region of icy bodies and dwarf planets, remnants from the solar system's formation 4.6 billion years ago. Pluto lives out there, along with hundreds of other objects large enough to have their own names, and thousands more we've barely begun to catalogue. This region extends perhaps 50 times Earth's distance from the Sun, a frontier we're only beginning to explore. And beyond even that, perhaps as far as 100,000 times Earth's distance from the Sun, stretches the Oort cloud, a theoretical sphere of frozen comets surrounding our entire solar system like a cosmic shell. Try to picture that for a moment. All the planets you know, all the familiar names and images, occupy just the innermost fraction of the Sun's true domain. The rest is darkness and ice, and objects so distant that sunlight barely touches them, so cold that the chemistry of life as we understand it couldn't even begin. This is where things hide. This is where a world could exist for billions of years without drawing our attention, because the spaces are so vast and the light so dim that finding anything requires patience, precision, and more than a little bit of luck. We've only known about some of these regions for a few decades. The Kuiper belt wasn't confirmed to exist until 1992, when astronomers finally detected the first objects beyond Neptune and Pluto. Before that, we suspected it was there, but we couldn't prove it. The Oort cloud remains theoretical even now, inferred from the behavior of comets that dive into the inner solar system from seemingly impossible distances. Our maps are incomplete. Our census is unfinished. And that's precisely why the question we're asking tonight isn't as absurd as it might first seem. The emptiness between worlds isn't truly empty, of course. It's filled with smaller things, rocky asteroids and icy comets, grains of dust and invisible fields of radiation. But finding something planet-sized out there, something substantial and solid, something that could cast a shadow if any light reached it, that's a different challenge entirely. It requires looking in the right place at the right time with the right tools. And it requires understanding that absence of evidence isn't evidence of absence. Just because we haven't seen something doesn't mean it isn't there, waiting in the spaces we haven't yet searched thoroughly enough. History has taught us this lesson before, sometimes in ways that made astronomers feel rather foolish for their assumptions. There was a time when we thought we knew all the planets, when the solar system seemed complete and accounted for. And then, someone noticed something odd, a discrepancy in the orbit of another world, a mathematical puzzle that didn't quite solve, and that small anomaly led to the discovery of an entire planet we'd somehow missed, a world that had been orbiting the Sun the whole time, just beyond our awareness. The story of Neptune is a good place to start, because it demonstrates something important about how we find hidden worlds. In the early 1800s, astronomers knew about Uranus, that pale blue-green planet discovered by William Herschel in 1781. It was the first planet discovered with a telescope, a triumph of human ingenuity and curiosity. But as decades passed and observers tracked Uranus carefully, noting its position night after night, something seemed wrong. Its orbit didn't quite match the predictions. It wandered slightly, drifting ahead of where calculations said it should be, then falling behind. These weren't random errors. They showed a pattern, a rhythm, as if something was tugging on Uranus, speeding it up at certain points in its orbit and slowing it down at others. Some astronomers suggested their calculations were wrong, that perhaps Newton's laws of gravity needed adjustment. But others, including a French mathematician named Urbain Le Verrier and an English astronomer named John Couch Adams, had a bolder idea. What if there was another planet out there, farther from the Sun than Uranus, massive enough that its gravity was perturbing Uranus's orbit? What if the anomaly wasn't an error, but a clue? Using nothing but mathematics, just pencil and paper, and the laws of celestial mechanics, Le Verrier calculated where this hypothetical planet should be. He predicted its mass, its distance, even its position in the sky at a specific moment. In September 1846, an astronomer in Berlin pointed his telescope at the coordinates Le Verrier had specified. And there it was, Neptune, a world so distant it takes 165 years to complete a single orbit around the Sun, invisible to the naked eye, yet massive enough to betray its presence through the subtle gravitational fingerprints it left on its neighbour. It was a stunning achievement, one that validated the power of mathematical prediction and demonstrated that we could find planets we couldn't see by observing their effects on things we could see. The universe leaves clues. Gravity writes signatures across space. And if you're patient and careful enough, you can read those signatures and deduce what must be there, even in darkness so profound that light itself seems to give up. Pluto's discovery in 1930 followed a similar path, though the story is a bit more complicated. Astronomers thought they saw irregularities in Neptune's orbit, similar to what had revealed Neptune itself. So they searched for yet another planet, a trans-Neptunian world that might explain the wobbles. Clyde Tombaugh, a young astronomer working at Lowell Observatory in Arizona, spent months photographing the same patches of sky, comparing images taken days apart, looking for anything that moved against the background stars. And he found Pluto, small and distant, orbiting in the outer dark. Here's the interesting part, though. Pluto turned out to be far too small to cause the orbital perturbations astronomers thought they'd detected in Neptune. Those perturbations were probably just errors in measurement, artifacts of the limitations of early 20th century instruments. Pluto was found by luck as much as prediction, a case of searching for something that didn't quite exist and stumbling across something real, but unrelated. It's a reminder that the universe doesn't always cooperate with our expectations, but sometimes it offers surprises that are just as valuable. For decades after Pluto's discovery, we thought we were done. 9 planets, the solar system was complete. But then came better telescopes, more sensitive cameras, and the realization that Pluto wasn't alone out there. The Kuiper belt revealed itself, populated by hundreds of objects similar to Pluto in size and composition. In 2005, astronomers discovered Eris, an icy world even more massive than Pluto, orbiting far beyond Neptune. This discovery forced a reckoning. Either we had to add Eris to the list of planets, along with every other large Kuiper belt object we might find, or we had to redefine what planet meant. In 2006, the International Astronomical Union chose the second option. Pluto was reclassified as a dwarf planet, a decision that upset many people who'd grown up learning 9 planets and felt a strange attachment to the small, distant world at the edge of the solar system. But the reclassification wasn't about diminishing Pluto. It was about acknowledging that our understanding had grown, that the solar system was more complex and interesting than we'd realized, and that simple categories couldn't capture the diversity of worlds orbiting our sun. So here we are, in an era where we know about 8 planets and dozens of dwarf planets and thousands of smaller objects, all orbiting in a vast region that extends billions of miles from the sun. We've mapped much of this territory. We've photographed comets and asteroids. We've sent spacecraft to fly past Pluto, capturing images of its icy mountains and nitrogen plains. We've learned an enormous amount. And yet, for all that knowledge, there are hints, whispers really, suggestions that we might still be missing something significant. Around 2014, astronomers began noticing something peculiar about certain objects in the outer solar system. These weren't just random icy bodies. They were the most distant objects known, orbiting far beyond Neptune in the scattered disk and inner Oort cloud regions. And their orbits showed an unexpected pattern. Instead of being randomly oriented, as you'd expect from objects scattered by ancient gravitational interactions, these orbits seemed to cluster together. They all reached their farthest points from the Sun in roughly the same region of space, and their orbital planes were tilted in similar ways. It was subtle, easy to dismiss as coincidence or observational bias. After all, we've only discovered a handful of these extremely distant objects, and maybe we're just finding the ones that are easier to detect because of where their orbits happen to take them. But as more objects were discovered, the clustering persisted. It seemed to be real, a genuine pattern demanding explanation. And when astronomers ran computer simulations trying to reproduce this clustering through random processes, they consistently failed. Something was organizing these distant orbits. Something massive was exerting gravitational influence, gently shepherding these objects into aligned paths. It's worth noting that not all astronomers agree the clustering is real. Some studies, analyzing observational biases in how these distant objects are discovered, have suggested the pattern might be an artifact of where and how we search. The debate continues in scientific journals and conferences, with researchers on both sides presenting evidence for their interpretations. But other analyses continue to find the clustering statistically significant, making this an active area of scientific investigation where the final answer hasn't yet been determined. The objects in question have wonderful names. Sedna, discovered in 2003, takes over 11,000 years to orbit the Sun once, coming as close as 76 times Earth's distance from the Sun at its nearest approach, then swinging out to a distance of about 937 times Earth's distance at its farthest point. 2012 VP-113 never comes closer to the Sun than Neptune's orbit and ventures even farther than Sedna at its most distant. These are worlds of eternal twilight, places where the Sun appears as merely the brightest star in the sky, offering negligible warmth and barely enough light to cast a shadow. What could cause such distant objects to orbit in coordinated ways? Random interactions with Neptune during the solar system's youth might explain some of it, but the math doesn't quite work for the most extreme cases. Gravitational interference from nearby stars passing through the outer solar system billions of years ago might contribute, but again, the effect seems too subtle and too specific. The most compelling explanation, according to many planetary scientists, is both simple and profound. There might be another planet out there, a large one, something with enough mass to gravitationally shape the orbits of these distant objects over millions of years, creating the clustering pattern we observe. In 2016, two astronomers at Caltech, Konstantin Batygin and Mike Brown, published a paper that sent ripples through the astronomical community. Using detailed computer simulations and mathematical analysis, they argued that the observed clustering of trans-Neptunian orbits could best be explained by the presence of an undiscovered planet, perhaps 5 to 10 times Earth's mass, orbiting 20 times farther from the Sun than Neptune. They called it Planet 9, and their calculations suggested it should be out there right now, slowly making its way around the Sun on an elongated orbit that takes perhaps 10,000 to 20,000 years to complete. Think about what that means for a moment. A world perhaps larger than Earth, substantial enough to have a solid surface, maybe even an atmosphere, has been orbiting our Sun for 4.6 billion years, since the solar system first formed. If this interpretation of the data is correct, it's been there the whole time, through every moment of human history, through the rise and fall of civilizations, through the first time someone looked up and wondered about those moving lights against the stars. It's been there, silent and unseen, while we built telescopes and launched spacecraft and convinced ourselves we understood our cosmic neighborhood. If you find this gentle drift through astronomical mysteries soothing, or if it helps your thoughts slow down and settle into something quieter, it would mean a great deal if you gave this video a like or subscribed, or simply let it play softly in the background. This quiet corner of science and wonder grows through small acts of support, and knowing that others find comfort in these questions, in this patient exploration of darkness and possibility, makes the work feel worthwhile. Thank you for being here, for listening, for letting these thoughts about hidden worlds drift through your mind as you ease toward rest. Now the question becomes more specific, more urgent in its implications. Could this hidden planet, this Planet 9, if the hypothesis proves correct, be Earth-like? Could it harbor conditions similar to our own world, with liquid water and stable temperatures, and perhaps even the chemistry necessary for life? Or is it doomed to be a frozen giant, a super-Earth made of rock and ice, eternally locked in darkness so profound that the Sun barely registers as a source of heat? These questions take us deeper into the nature of what makes a world habitable, what distinguishes Earth from the countless other rocky bodies in the universe, and whether the specific conditions we enjoy here could possibly exist at such extreme distances from our star. These questions take us deeper into the nature of what makes a world habitable, what distinguishes Earth from the countless other rocky bodies in the universe, and whether the specific conditions we enjoy here could possibly exist at such extreme distances from our star. To understand the possibility of another Earth in our solar system, we need to explore what astronomers have calculated about this potential hidden world, how they're searching for it, and what characteristics it might actually possess. The Planet 9 hypothesis didn't emerge from a single observation or a sudden insight. It grew from years of careful work, from tracking the movements of dozens of distant objects, from noticing patterns that seemed too consistent to be coincidental. Konstantin Batygin and Mike Brown, the astronomers who brought this theory into mainstream scientific discussion, spent months running computer simulations, testing different scenarios, trying to understand what could produce the orbital clustering they were seeing in the data. Their calculations pointed to something specific and startling. The hypothetical planet would need to be quite massive, somewhere between 5 and 10 times Earth's mass, making it what astronomers call a super-Earth. This would place it in an interesting category, larger than Earth, but smaller than the ice giants Uranus and Neptune. No planet like this exists in the inner solar system, but super-Earths are actually quite common around other stars. We've discovered thousands of them orbiting distant suns, suggesting that planets of this size form readily under the right conditions. The orbit Bataille and Brown calculated is extraordinary in its strangeness. If their models are correct, Planet 9 would follow an elongated elliptical path, coming perhaps 200 to 300 times Earth's distance from the Sun at its closest approach, then swinging out to 600 or even 800 times that distance at its farthest point. To put that in perspective, Neptune orbits at about 30 times Earth's distance from the Sun. This hypothetical world would spend most of its time vastly farther out, drifting through regions we've barely begun to explore. Places where sunlight arrives so weakened that high noon would feel like deep twilight on Earth. One complete orbit might take anywhere from 10,000 to 20,000 years. Think about that timescale for a moment, as you lie there in the comfort of your own brief moment in cosmic time. Since the last ice age ended on Earth, since humans first began farming and building permanent settlements about 12,000 years ago, this planet, if it exists, might have completed just one journey around the Sun. Entire civilizations could rise and fall in the time it takes for this world to experience a single year. The pyramids of Egypt, standing for 4,500 years, represent less than half of a Planet 9 summer. The orbital plane would be tilted as well, inclined somewhere between 15 and 20 degrees relative to the plane where most planets orbit, according to the most recent analyses by Bataille and Brown. This means Planet 9 doesn't circle the Sun in the same flat disk as Earth and Jupiter and the others. It follows its own path, diving below and rising above the ecliptic plane like a marble rolling around the inside of a tilted bowl. This unusual orientation is actually part of what makes it so hard to find, because it could be almost anywhere in a vast three-dimensional space, not confined to the relatively narrow band where we normally search for planets. The gravitational influence this planet would exert on distant objects is subtle but measurable, if the hypothesis is correct. It wouldn't dramatically fling comets around or destabilize orbits in obvious ways. Instead, over millions of years, its gravity would gently tug on objects as they pass, nudging them into slightly different paths, creating the clustering pattern that first suggested its existence. It's like detecting a person in a dark room not by seeing them directly, but by watching how papers on a desk flutter when they walk past, or hearing the creak of floorboards under their weight. Indirect evidence, circumstantial perhaps, but compelling when all the pieces fit together. Of course, not all astronomers are convinced. Science thrives on skepticism, on the insistence that extraordinary claims require extraordinary evidence. Some researchers argue that the clustering of distant orbits might be observational bias, that we're simply finding objects in certain regions because that's where we happen to be looking most carefully. Others suggest alternative explanations, exotic physics or multiple smaller objects instead of one large planet. The debate continues, conducted in research papers and conferences, a patient argument about mathematics and probability and what can be concluded from limited data. But the hypothesis persists because it keeps making testable predictions. Bataille and Brown didn't just say a planet might exist. They calculated where it should be at different points in time, what effects it should produce on other objects, even what its physical characteristics might be based on its mass and distance. These predictions can be checked, tested, potentially proven wrong, and so far, despite years of searching, nothing has definitively ruled out Planet 9's existence. The hypothesis remains alive, a puzzle waiting for its final piece. So how exactly do you search for a planet that might be 500 times farther from the Sun than Earth, that reflects almost no light, that moves so slowly across the sky that its position barely changes from year to year? The challenge is enormous, almost overwhelming. It's like trying to find a single black pebble on a beach at midnight, without a flashlight, when you're not even certain the beach is the right one or whether the pebble exists at all. And yet, astronomers are searching, using some of the most powerful telescopes on Earth, dedicating precious observation time to this cosmic hunt. The primary method involves taking repeated photographs of large sections of the sky, then comparing those images carefully to detect anything that moves. This is essentially the same technique Clyde Tombaugh used to find Pluto in 1930, though the technology has advanced considerably. Modern digital cameras can capture images far more sensitive than photographic plates, and computers can analyze millions of data points, looking for the telltale shift of an object moving against the background stars. but the scale of the search has also grown proportionally more daunting. Planet 9, if it exists at its predicted distance, would be extraordinarily faint. At best, it might reflect only a tiny fraction of the sunlight that reaches it, appearing perhaps 100,000 times dimmer than Neptune, itself invisible to the naked eye. It would be fainter than many asteroids, fainter than distant galaxies, lost in a sky crowded with millions of other faint objects that also need to be catalogued and tracked. Finding it requires distinguishing one particular dim point of light from countless others, recognizing that this specific speck among all the specks is actually a nearby planet rather than a distant star or galaxy. The movement is the key signature, but that movement is glacially slow. Based on the predicted orbit, Planet 9 might drift across the sky at a rate of perhaps half a degree per year, moving a distance equivalent to the width of the full moon over several months. You need images taken weeks or months apart to detect this motion reliably, and you need to be looking at the right patch of sky at the right time. The planet's orbit is so elongated that it spends most of its time in the farthest, darkest reaches, moving slowly. Only when it's closer to the Sun, during its brief perihelion passage, might it be bright enough and fast enough to detect with current technology. Several major surveys are actively searching. The Subaru telescope in Hawaii, one of the largest optical telescopes in the world, has been conducting dedicated searches of the northern sky, systematically photographing regions where Planet 9 might lurk. The Dark Energy Survey, though primarily focused on understanding cosmic expansion, has also surveyed large areas of the southern sky that might contain the planet. Each survey generates terabytes of data, images that must be processed, analyzed, cross-referenced, each point of light examined to determine whether it might be the world everyone is looking for. Infrared observations offer another possibility. All objects emit thermal radiation based on their temperature, and a planet the size of Planet 9 would retain some internal heat from its formation billions of years ago, plus heat generated by radioactive decay in its core. This means it might be slightly warmer than its surroundings, enough to emit faint infrared light that could be detected by sensitive instruments. NASA's WISE mission, a space telescope that surveyed the entire sky in infrared wavelengths, captured data that astronomers have analyzed searching for Planet 9's thermal signature. So far, nothing conclusive has emerged, but the search continues with more sensitive instruments. There's also the possibility of using future telescopes. The Vera C. Rubin Observatory in Chile, which is preparing to begin full operations, will survey the sky with a camera capable of photographing the entire visible sky every few nights, creating a constantly updated map of the universe. If Planet 9 exists anywhere in the regions this telescope can observe, its movement will eventually be detected through the accumulation of repeated observations. It's a patient strategy, letting time and technology work together to reveal what's hidden. But here's the frustrating reality of the search. The area of sky that needs to be covered is vast, thousands of square degrees, and the planet could be anywhere within that enormous region. It's not like searching a closet where you can systematically check each shelf. The search volume is three-dimensional, extending to different distances, and the target might be at any point within that volume. Even with the best telescopes and the most sophisticated analysis, finding Planet 9 might take years or decades, assuming it exists at all. It's a hunt that requires patience, persistence, and the acceptance that you might search for a lifetime without success. As you rest there, perhaps you can appreciate the strange determination of astronomers who dedicate their careers to questions like this, who spend cold nights at remote telescopes, pointing instruments at empty regions of sky, looking for something that might not exist, guided only by mathematical predictions and the faint hope that the universe will reveal another secret. There's something quietly beautiful in that dedication, in the willingness to search the darkness simply because the possibility exists, because not knowing is more uncomfortable than the risk of being wrong. Now, let's consider the deeper question that underlies this entire search. If Planet 9 exists, could it be Earth-like in any meaningful sense? Could it share characteristics with our own world, the specific conditions that make Earth not just a ball of rock, but a place where complexity and change, and perhaps even life, can flourish? This question takes us into the heart of what we understand about planetary habitability, about the narrow range of conditions that seem necessary for worlds to support the chemistry of life as we know it. Earth sits in what astronomers call the habitable zone, sometimes colloquially known as the Goldilocks zone. Not too hot, not too cold, but just right for liquid water to exist on the surface. This zone extends roughly from Venus's orbit to perhaps just beyond Mars, a relatively narrow band where a planet receives enough sunlight to prevent water from freezing solid, but not so much that it boils away. Water is essential for life as we understand it, the solvent in which organic chemistry occurs, the medium in which the first self-replicating molecules likely emerged billions of years ago. Planet 9, orbiting hundreds of times farther from the Sun than Earth, would be nowhere near the habitable zone. At that distance, the Sun's warmth is negligible, less than 1/10,000th what Earth receives. Any water on the surface would be frozen solid, locked in ice so cold it behaves like rock. The average temperature might hover around -370 degrees Fahrenheit, cold enough that most gases would freeze, that methane and nitrogen would exist as ices rather than liquids or vapors. In terms of surface habitability, by Earth standards, Planet 9 would be utterly inhospitable, a frozen wasteland where nothing we would recognize as life could survive. But Earth-like doesn't necessarily mean habitable. It might mean structural similarities, compositional resemblances, features that remind us of home even if they exist in a profoundly different context. A super-Earth at Planet 9's distance might have a rocky core, like Earth, compressed by immense gravitational pressure into exotic high-density minerals that don't exist in our planet's mantle. It might have a thick atmosphere, though that atmosphere would be frozen into layers of ice on the surface, nitrogen snow and methane frost accumulating over billions of years. It might even have something resembling plate tectonics, the slow churning of crustal plates driven by internal heat. Earth's plate tectonics are powered by radioactive decay in the mantle and residual heat from the planet's formation. A larger planet would have more radioactive elements, generating more internal heat, potentially enough to keep the interior molten even while the surface remains frozen. This could create volcanic activity, ice geysers, regions where internal heat breaks through the frozen crust, creating temporary lakes of liquid water buried beneath miles of ice. This scenario isn't purely theoretical. We see something similar on some of Jupiter's and Saturn's moons. Europa, a moon of Jupiter about the size of Earth's moon, has an icy surface covering what scientists believe to be a global ocean of liquid water kept warm by tidal heating from Jupiter's gravity. This subsurface ocean was inferred through magnetic field measurements by NASA's Galileo spacecraft, which detected signatures suggesting a layer of electrically conductive salty water exists beneath the ice. Enceladus, a small moon of Saturn, has geysers that shoot plumes of water vapor into space, suggesting a subsurface ocean beneath its frozen exterior. If small moons can maintain liquid water through internal heating, perhaps a super-Earth, with its larger mass and greater store of internal heat, could do so as well, even at Planet 9's distance. So when we ask if there could be another Earth hidden in our solar system, the answer depends on what we mean by Earth-like. A surface world with blue skies and green landscapes and liquid oceans exposed to sunlight? Almost certainly not. But a rocky planet with internal differentiation, with a molten core generating a magnetic field, with subsurface oceans where liquid water exists and where the chemistry of life might possibly occur? That becomes more interesting. That enters the realm of possibility, a scenario that doesn't violate any known laws of physics, that fits within our understanding of how planets form and evolve. The formation history matters too. Planet 9, if it exists, probably didn't form where it is now. Most planetary scientists believe it would have formed much closer to the Sun, perhaps in the region between Saturn and Neptune, during the chaotic early period when the solar system was still arranging itself. Gravitational interactions with Jupiter, powerful and violent, might have ejected it outward, flinging it into the deep freeze of the outer solar system, where it settled into its current elongated orbit. This ejection event would have been traumatic, potentially stripping away any primordial atmosphere, resurfacing the planet through impacts and tidal heating. But planets are resilient. Earth itself endured tremendous violence early in its history, including a collision with a Mars-sized object that blasted enough material into orbit to form the Moon. That impact melted Earth's entire surface, vaporized rock, created a temporary atmosphere of rock vapor. And yet, Earth recovered. It cooled, reformed, developed a new atmosphere through volcanic outgassing, eventually became the stable world we know. If Earth could survive such catastrophe, perhaps Planet 9, if it was ejected outward, could also rebuild itself, creating a new equilibrium in its frozen exile. The question of what this world might look like, if we could somehow visit it, creates images that blend the familiar and the alien. Imagine standing on a plain of water ice, hard as granite beneath your feet, extending to a horizon much farther away than Earth's. Because the planet is larger, its curvature gentler. The sky would be black, or perhaps very dark blue, with stars visible even in daytime because there's so little atmosphere to scatter light. The sun would be a bright star, brighter than any other, but offering no warmth, no comfort, just a reminder of how far you are from home. If the planet has a thin atmosphere of nitrogen or methane, it might create faint colors during sunrise or sunset, which would last for years given the planet's slow rotation. There might be mountains of ice, valleys carved by ancient glaciers of frozen nitrogen, crater fields from billions of years of impacts. If volcanic activity exists, you might see dark patches where heat has melted through the ice, creating temporary lakes that refreeze slowly, layer upon layer, building up like strange geological scars. It would be a world of stillness, of silence, of cold beyond human endurance, yet still a world, still a place with features and textures and a history written in ice. But we should be careful not to limit our thinking to just one possibility. The Planet 9 hypothesis, compelling as it is, isn't the only explanation for the orbital clustering of distant objects. Science progresses by considering alternatives, by testing different ideas against the evidence, by remaining open to unexpected answers. And there are other theories, other potential hidden worlds or phenomena that might account for what we're seeing in the outer solar system. One alternative suggests not a single massive planet, but several smaller objects, perhaps Neptune mass or slightly smaller, orbiting in the outer reaches. Multiple planets could collectively produce gravitational effects similar to one large planet, and might be easier to hide because each individual world would be fainter and harder to detect. This scenario is more complex, requiring specific orbital configurations to create the observed clustering, but it's not impossible. In fact, computer simulations show that under certain conditions, multiple planets could remain stable over billions of years, shepherding distant objects into aligned orbits. Then there's the modified Newtonian dynamics hypothesis, usually abbreviated as MOND. This is a more radical idea that challenges our basic understanding of gravity. MOND suggests that Newton's and Einstein's laws of gravity, which work perfectly well in most situations, might need modification at very low accelerations, like those experienced by objects in the far outer solar system. Under MOND, the clustering of distant orbits wouldn't require a hidden planet at all. It would emerge naturally from different gravitational physics. Most physicists are skeptical of MOND, but it remains a possibility, a reminder that even our most fundamental physical laws might be approximations rather than final truths. There's also been speculation about primordial black holes. These are hypothetical objects that might have formed in the first fraction of a second after the Big Bang, when the universe was incredibly dense and hot. A primordial black hole with a few times Earth's mass would be tiny, perhaps the size of a grapefruit, but it would exert the same gravitational influence as Planet 9. If such an object were captured by the Sun during the solar system's formation, it would orbit invisibly, affecting distant objects through its gravity, while remaining essentially undetectable by conventional telescopes. It's a long shot, almost science fiction, but not entirely impossible. Some researchers have proposed that the clustering might not be caused by a single object at all, but rather by the cumulative effect of countless smaller bodies in the Kuiper belt and scattered disk. If the total mass of these objects is larger than we currently estimate, their combined gravity might be enough to shape the orbits of the most distant known objects. This would mean Planet 9 doesn't exist, that what we're seeing is just the natural gravitational architecture of the outer solar system's debris field. It's a more conservative explanation, requiring fewer assumptions, though it struggles to explain the specific details of the orbital clustering. Each of these alternatives has its proponents and its critics. Each offers a different window into how the solar system might be organized, how gravity and motion and time weave together to create the patterns we observe. The scientific process will eventually distinguish between them through new observations, better data, more refined calculations. But for now, they coexist as possibilities. Different stories we can tell about the darkness beyond Neptune, each internally consistent, each waiting for reality to confirm or deny it. The search for Planet 9, or whatever might be hiding in the outer solar system, is really a search for understanding. It's about completing our picture of how planets form and migrate, about testing our theories against the actual architecture of our cosmic home, about confronting the humbling fact that even after centuries of astronomy, we still don't know everything that orbits our own sun. There's a particular kind of excitement in that uncertainty, a feeling that discovery is still possible, that the universe hasn't given up all its secrets yet, that patience and curiosity might still be rewarded with glimpses of something new. As you lie there, feeling the quiet tug of sleep beginning to soften your thoughts, perhaps you can hold that sense of possibility gently in your mind. Somewhere out there, in the cold and the dark, beyond where any telescope has yet looked carefully enough, there might be worlds we haven't found. Planets that have been orbiting our sun since before Earth cooled enough for the first oceans to form, since before life emerged, since before anything like human consciousness existed to wonder about distant spaces. They've been there all along, patient and silent, waiting for us to notice, to calculate, to point our instruments in the right direction and finally see what's been hidden in plain sight. They've been there all along, patient and silent, waiting for us to notice, to calculate, to point our instruments in the right direction and finally see what's been hidden in plain sight. And that brings us to the true edge of our solar system, to regions so distant and dark that even the concept of distance begins to lose meaning, where time stretches and patience is measured not in years, but in millennia. When we think about the solar system's boundaries, we tend to imagine Neptune's orbit as the frontier, the last outpost before deep space begins. But that's a human convenience, a psychological border rather than a physical one. The sun's gravitational influence extends far beyond Neptune, reaching out into a vast sphere of space that dwarfs the planetary region we're familiar with. To understand where a hidden planet might exist, we need to journey outward in our minds, past all the familiar landmarks, into regions where the very idea of the solar system transforms into something stranger and more mysterious. Beyond Neptune lies the Kuiper belt, which we've mentioned before, a region of icy debris extending from about 30 to 50 times Earth's distance from the Sun. This is where Pluto orbits, along with other dwarf planets like Haumea and Makemake, and hundreds of thousands of smaller objects, most of them just a few miles across. These are the remnants of planetary formation, icy building blocks that never quite coalesced into a full planet because Jupiter's gravity disrupted the region during the solar system's youth. They orbit in relative peace now, occasional collisions sending fragments spiraling inward to become comets that light up our skies. But the Kuiper belt is just the beginning. Beyond it lies the scattered disk, a more chaotic region where objects follow highly elliptical orbits, swooping in toward Neptune then racing back out to incredible distances. Eris orbits here, coming as close as 38 times Earth's distance from the Sun, but venturing out to 98 times that distance at its most remote. Sedna, that mysterious object we mentioned earlier, barely touches the scattered disk, spending most of its time in a region even more distant, a transitional zone between the scattered disk and what lies beyond. And what lies beyond is something so vast it challenges comprehension. The Oort cloud, named after Dutch astronomer Jan Oort, who first theorized its existence in 1950, is believed to be a spherical shell of trillions of icy objects surrounding the entire solar system. It begins perhaps 2,000 to 5,000 times Earth's distance from the Sun, where light from our star takes between 10 and 28 days to arrive, and extends outward to maybe 100,000 times that distance, where sunlight takes perhaps a year and a half to reach, halfway to the nearest star. This is interstellar space, the true frontier where our sun's domain fades into the realm of other stars. The Oort cloud objects are too distant and too faint to observe directly with current technology. We infer its existence from the behavior of comets, those spectacular visitors that occasionally fall into the inner solar system, trailing tails of gas and dust. Long-period comets, the ones that take thousands or millions of years to orbit the Sun, appear to originate from the Oort cloud, knocked loose from their distant perches by gravitational perturbations from passing stars or tidal forces from the galaxy itself. Each comet is a messenger from this hidden realm, a frozen time capsule from the solar system's birth that spent billions of years in cold storage before its brief moment in the Sun. Imagine the Oort cloud not as a belt or a disk, but as a vast bubble surrounding everything we think of as the solar system. The planets, the Kuiper belt, the scattered disk, all exist in a tiny central core of this bubble, like a marble sitting at the center of a cathedral. The space in between, that enormous volume, is thought to be populated by countless icy bodies, each one following its own lonely orbit, rarely if ever interacting with anything else. They drift through darkness so profound that the sun appears as nothing more than a bright star, offering no warmth whatsoever, just a point of light slightly brighter than the stellar background. If Planet 9 exists, it would orbit somewhere between the scattered disk and the inner Oort cloud, in that transitional zone where the solar system hasn't quite ended but where familiar structures have dissolved into something more ambiguous. At its farthest point, based on current models, it might venture as far as 600 to 800 times Earth's distance from the Sun, deep into a region where gravitational influences from nearby stars begin to compete with the Sun's pull. It would be a true frontier world, existing at the very edge of what we can meaningfully call our solar system, tenuously bound to the Sun, orbiting so slowly that its motion would be imperceptible on human timescales. The question of what defines the solar system's edge is more philosophical than scientific. Is it the distance where the Sun's gravity can no longer hold objects in orbit? That would place the boundary somewhere in the outer Oort cloud about 2 light-years from the Sun. Is it where the solar wind, that stream of charged particles flowing outward from the Sun, finally meets the interstellar medium and forms the heliopause? That boundary sits about 120 times Earth's distance from the Sun, a region NASA's Voyager 1 spacecraft crossed in 2012, becoming the first human-made object to enter interstellar space. Or is it simply where the Sun's light fades to the point of irrelevance, where you can no longer distinguish it from other stars? That's a subjective measure, dependent on how sensitive your eyes are and what you consider significant illumination. Each definition creates a different boundary, a different sphere of influence. And within those nested spheres, there's room for countless hidden objects, planets and dwarf planets and comets we haven't discovered yet. Each one part of the Sun's family, but so remote that detecting them requires technology and patience beyond what we currently possess. The solar system is larger than we once imagined, and stranger, filled with populations of objects we're only beginning to census, organized by gravitational architectures we're still working to understand. One of the most humbling aspects of this search is the timescale involved. If Planet 9 is discovered tomorrow, confirmed through repeated observations, its orbit calculated precisely, we would still know remarkably little about it. We couldn't send a spacecraft there, not with current technology. The journey would take decades or centuries, requiring propulsion systems that don't exist yet and power sources that could function across interstellar distances. We couldn't even study it in detail with telescopes because it's simply too faint and too far away to reveal surface features or atmospheric composition. We would know it exists, we would know its size and orbit, but it would remain fundamentally mysterious, a world we can see only as a point of light, a mathematical abstraction made real. And perhaps that's fitting. Perhaps some mysteries are meant to remain partially unsolved, hovering at the edge of our knowledge, reminding us that the universe is larger than our ability to explore it fully. There's a certain beauty in that limitation, in knowing that no matter how advanced we become, there will always be places too distant to visit, objects too faint to study closely, questions that remain tantalizingly just beyond our grasp. It keeps us humble. It keeps us curious. It ensures that wonder has room to flourish. The search for hidden planets in our solar system connects to broader questions about planetary systems in general. We now know that our solar system isn't typical, at least not compared to the thousands of exoplanetary systems we've discovered orbiting other stars. Many of those systems have hot Jupiters, massive planets orbiting close to their stars where Mercury should be. Others have super-Earths, that intermediate size between Earth and Neptune that doesn't exist in our system's inner regions. Still others have planets in compact configurations, with multiple worlds packed tightly together in orbits that would fit inside Mercury's path around the Sun. Our solar system, with its orderly progression from small rocky planets to gas giants, with relatively wide spacing and circular orbits, appears to be somewhat unusual, and that raises questions. Is our configuration rare because it's unstable, and systems like ours tend to rearrange themselves through gravitational interactions? Or is it rare because the conditions that produce this architecture are uncommon? And if Planet 9 exists, ejected from the inner system during the solar system's youth, does that make our story more typical? Evidence of the same kind of planetary migration and ejection we see in other systems? These questions matter for understanding how common Earth-like planets might be in the universe. If our solar system's architecture is unusual, if the stable circular orbits that allow Earth to maintain consistent temperatures year after year are rare, then perhaps habitable planets are rarer than we hoped. But if our system is actually more typical than it appears, if most solar systems go through chaotic early periods that eject some planets and stabilize others, then perhaps the conditions for life are more common than we currently believe. Planet 9 in this context isn't just a curiosity. It's a clue to broader patterns in planetary system formation, a data point in the vast experiment of cosmic evolution. As you rest there, your breathing slowing, your thoughts beginning to drift, consider what it means that we ask these questions at all, that we look at the darkness and wonder what's hidden there, that we build instruments and develop theories and spend years searching for worlds we've never seen, guided only by mathematics and the conviction that understanding is valuable for its own sake. There's something distinctly human in that impulse, something that distinguishes us from every other form of life we know. A tree doesn't wonder what lies beyond the forest. A whale doesn't contemplate the ocean's boundaries. But humans, fragile and short-lived as we are, look up at the night sky and ask questions that stretch across billions of miles and billions of years. We create maps of regions we'll never visit. We calculate the orbits of objects we'll never touch. We imagine worlds existing in darkness so profound that light itself becomes a rare and precious thing. And we do this not because it offers immediate practical benefit, but because understanding the universe seems to be woven into what we are, into the very structure of consciousness itself. The hunt for Planet 9 exemplifies this distinctly human quality. It requires patience beyond individual lifetimes, telescopes that represent the collective effort of thousands of people, mathematical frameworks developed over centuries. One person proposes a hypothesis, another tests it with observations, a third builds the instrument that might detect what the first person predicted. None of them will see the full story completed in their lifetime. None of them will know the final answer with certainty during their careers. But they contribute their piece, add their small increment to the growing body of knowledge, trusting that future generations will build on their work, will carry the search forward, will eventually answer the questions they could only pose. This is why planetary science matters, even when it seems abstract or disconnected from daily life. It's not about finding resources to exploit or places to colonize, at least not primarily. It's about understanding our context, our place in the larger scheme of cosmic architecture. It's about recognizing that Earth, for all its importance to us, is just one world among countless others, that the processes that shaped our planet are universal, operating everywhere stars form and planets accrete. When we search for hidden planets in our solar system, we're really searching for pieces of our own origin story, for clues about how we came to exist in this particular place at this particular time. And there's comfort in that search, oddly enough, comfort in knowing that the universe is consistent, that the same laws of physics operate here and in the most distant reaches of space. Comfort in the idea that we're not separate from the cosmos but part of it, made of the same elements, shaped by the same forces, subject to the same fundamental principles. When we look for Planet 9, we're looking at family, at a sibling world that formed from the same cloud of gas and dust that created Earth, that's been orbiting the same sun for the same 4.6 billion years, just in a different room of the same vast house. The ethical dimension of this search is worth considering too, as your mind softens and thought becomes less linear. We live in an era where human activity affects the entire planet, where we can see the consequences of our choices written in melting ice and rising seas and changing weather patterns. In that context, what's the value of searching for distant planets? Shouldn't we focus all our attention and resources on solving immediate problems, on ensuring our own survival rather than indulging curiosity about worlds we'll never reach? But perhaps it's not an either-or proposition. Perhaps the same qualities that drive us to search for hidden planets, curiosity and patience, and the willingness to work toward understanding that might take generations to achieve, are exactly the qualities we need to address long-term challenges here on Earth. Perhaps training ourselves to think on cosmic timescales, to care about things that won't matter in our lifetimes but will matter to future generations, creates the mental framework necessary for stewardship of our own planet. The skills we develop in studying distant worlds, the technologies we create, the collaborative international efforts we build, all of these have applications beyond pure science. And there's something else, something harder to quantify but perhaps equally important. Humans need hope. We need to feel that the future holds possibilities, that there are still discoveries to be made, frontiers to explore, questions whose answers will surprise and delight us. The search for Planet 9 offers that hope. It says that even now, even after centuries of astronomy, we haven't finished the most basic task of mapping our own solar system. It says that wonder is still possible, that the universe still has secrets to reveal, that patient observation might still be rewarded with the thrill of finding something that was there all along, hidden and waiting. As we drift toward the end of this long night's journey through space and speculation, let's return to the question we started with. Could there be another Earth hidden in our solar system? We've explored the evidence, the theories, the search methods, the alternative explanations. We've thought about what Earth-like might mean at such enormous distances from the Sun, and we've wandered through the outer reaches of the solar system, through the Kuiper belt and scattered disk and the beginnings of the Oort cloud, regions where darkness reigns and objects orbit in near-perfect isolation. The honest answer is that we don't know yet. The evidence suggests something might be out there, something substantial enough to affect the orbits of distant objects through its gravitational pull, but evidence isn't proof. The patterns we see might be real, or they might be artifacts of limited observations and observational biases. Planet 9 might exist exactly as calculated, or it might not exist at all, a mathematical ghost born from incomplete data. Science doesn't always provide immediate answers. Sometimes it offers probabilities, ranges of possibility, invitations to keep searching until certainty emerges from the fog of uncertainty. What we can say with confidence is that our solar system still holds mysteries, that the spaces between worlds aren't as empty or as well understood as we once believed, that gravity writes stories in the orbits of distant objects, and if we're patient enough and careful enough, we can read those stories and deduce what must be there, even when we can't see it directly. The tools exist, the methods are sound, and the will to search persists. The Vera Rubin Observatory in Chile, which released its first stunning images in June 2025 and is expected to begin full science operations by the end of this year, will survey the entire visible sky every few nights, creating a constantly updated map of anything that moves. If Planet 9 is real, if there is another substantial world orbiting our sun in the outer darkness, then eventually, probably within the next decade or two, it will likely be found. And when that happens, if it happens, the discovery will ripple through our understanding of planetary systems. It will force us to revise our models of solar system formation, to reconsider how common planetary migration and ejection might be. It will give us a new world to study, even if only from afar, a natural laboratory for understanding what happens to planets exiled to extreme distances from their star. It will expand the census of our cosmic family, adding another sibling to the planetary roster, proof that even home can surprise us if we look carefully enough. But even if Planet 9 doesn't exist, even if the search eventually concludes that the orbital clustering has some other explanation, the effort won't have been wasted. Science progresses as much through ruling things out as through discovering new truths. Negative results matter. They sharpen our understanding, eliminate possibilities, push us toward better theories and more refined observations. And the search itself drives technological development, creates new observational techniques, trains new generations of astronomers in the patient art of studying the sky. The process has value independent of the outcome. As you lie there now, feeling the weight of your body against whatever surface holds you, feeling the quiet rhythm of breath moving in and out, perhaps you can let these thoughts settle gently into rest. Somewhere out there, in the cold beyond Neptune, in the darkness where sunlight barely penetrates and time moves slowly enough that entire human civilizations rise and fall between one sunrise and the next, there might be worlds we haven't found yet, planets that have been part of our solar system since the beginning, that form from the same primordial cloud that created Earth, that have their own geology and chemistry and history completely unknown to us. They orbit in patient silence, these potential worlds, unaware that on one small planet much closer to the Sun, beings made of carbon and water have developed consciousness and curiosity and the ability to wonder about things they cannot see. They don't know that telescopes point outward, searching, that computers analyze images looking for their subtle movement against the stars. They simply exist, if they exist at all, following the gravitational paths carved out billions of years ago. spinning through their slow, lonely years in the dark. And there's something peaceful in imagining them there, something that matches the quiet of late evening and the soft descent into sleep. These distant worlds, real or hypothetical, ask nothing of us. They don't require our attention or our belief. They simply are or aren't, existing or not existing, independent of our awareness, indifferent to whether we find them or not. They're patient beyond measure because that's what the universe is. Patient and vast and operating on timescales that make our urgency seem like a flicker, like a single quick breath in an infinitely long exhale. You are here on Earth, on this one particular planet, in this one particular solar system, at this one particular moment in the 14 billion year history of the universe. And in this moment, you're connected to everything else, to the distant planets and the searching astronomers and the slow, patient wheeling of worlds through empty space. You're made of atoms forged in the hearts of ancient stars, breathing air that cycle through countless living things before reaching your lungs, thinking thoughts that emerge from the same fundamental physics that governs the orbit of hypothetical Planet 9. The question of whether another Earth exists hidden in our solar system is really just another way of asking who we are, where we come from, what our context is in the larger cosmic story. It's a question that leads outward into darkness, but also inward into meaning, into the recognition that we're part of something incomprehensibly large and old and intricate. Every planet, known or unknown, near or far, shares a common origin in clouds of gas and dust collapsing under their own gravity, forming stars and worlds, and the conditions for complexity to emerge. And here, on this one world, in this quiet moment, you can rest in that knowledge. You can let it be enough that the universe exists, vast and mysterious and still revealing itself at its own pace. You can close your eyes and feel the ancient rotation of Earth carrying you through space, the patient orbit around the Sun that's occurred 4.5 billion times since our planet first coalesced. You can breathe slowly and deeply, participating in the same chemical cycles that power all life, the exchange of oxygen and carbon dioxide that connects you to every green thing that's ever grown in sunlight. The search for hidden planets continues while you sleep. Telescopes operate through the night. Cameras capture images. Computers process data. Somewhere, an astronomer is comparing new observations to old ones, looking for the telltale shift of a distant object. Somewhere, a mathematician is refining orbital calculations, testing whether a planet with slightly different characteristics might better explain the patterns in the data. The work goes on, patient and methodical, driven by curiosity and the conviction that understanding matters, that finding truth is worth the effort, even when that truth is as simple as yes, there's another planet, or no, there isn't. And in the morning, or whenever you wake, the question will still be there, unanswered but approachable, a puzzle waiting for its solution. Planet 9 might be found tomorrow, or next year, or a decade from now, or never. The universe doesn't hurry. It unfolds at its own rate, revealing secrets when conditions align, when the right person looks at the right data with the right insight at the right moment. Until then, we wait and search and wonder and find comfort in the fact that some mysteries take time to solve, that patience is rewarded more often than urgency, that the best discoveries often come to those who can sit quietly with uncertainty and not demand immediate resolution. So rest now, gentle traveler, through space and time. Let your thoughts drift like those distant worlds, following their own quiet orbits, requiring no effort or intention. Let the darkness beyond your eyelids mirror the darkness beyond Neptune, soft and complete and strangely comforting. Let the question of hidden Earths float away into sleep, carried on the slow current of breath and the deeper current of time that moves through all things, wearing down mountains and building up stars and slowly, slowly bringing distant worlds into the light, where we can finally see them and know them and add them to the family of places that share our sun. The universe is patient. The planets are patient. And you can be patient too, resting in this moment, this breath, this small span of quiet before sleep takes you away to wherever consciousness goes when it stops paying attention to the world. Somewhere out there, maybe, a world waits, and here, right here, you wait too. And the waiting is enough because it's filled with wonder, with possibility, with the gentle acknowledgement that some questions are more valuable than their answers, that searching matters as much as finding, that the journey through darkness toward understanding is itself a kind of home. Thank you for drifting through this long night with me, for letting these thoughts about hidden worlds and patient searches accompany you toward rest. If this gentle exploration has helped you find a quieter place, if it's eased the transition from waking to sleeping, I hope you'll return again. There are always more questions to ask, more cosmic mysteries to wonder about, more ways that science can become a lullaby. Until then, sleep well, dream softly, and know that the universe keeps its secrets with kindness, revealing them only when we're ready, only when we've learned to look with both precision and wonder, with both rigor and reverence, with both our minds and our capacity for awe.